Es un honor para nosotros tener como invitada a Sarah Hart. Sarah Hart es la primera profesora que ocupa el puesto de geometría en el Colegio Graceman desde el 2020 lo ocupa. Es una posición que tiene 500 años. Es profesora emérita de matemáticas en Birkbeck, Universidad de Londres. Su trabajo de investigación es en el área de teoría de grupos y actualmente está muy involucrada con la Sociedad Británica de Historia de las Matemáticas. Fue presidenta de esta sociedad del 2021 al 23. Ha sido una gran comunicadora de las matemáticas y es muy buscada para dar conferencias públicas. Ella está interesada en los lazos entre matemáticas, cultura y creatividad. Su libro que aparece publicado en español en este pasado marzo, Érase una vez los números primos, la asombrosa relación entre la literatura y las matemáticas, ha tenido críticas muy buenas en periódicos importantes como el New York Times, The Observer, The Economics, The Washington Post y The Wall Street Journal. Hay un artículo interesante sobre ella en la revista Quantum Magazine. Welcome.
Thank you. Thank you very much for having me. I'm going to share my screen now and hopefully you will see it. Okay. So I begin. Okay. Okay, so I'm hoping everyone can see my screen and hear me. Thank you very much for inviting me today. I apologize that my Spanish is not good enough, or indeed good at all, to be able to speak to you in Spanish today. So thank you for allowing me to speak in English. This seminar, I'm delighted to be speaking at the seminar because the links between mathematics and the arts and the humanities, I think, are so important and don't get enough attention. We think of mathematics traditionally, it is put in a box with science. Of course, mathematics is incredibly useful for science. We often say it's the language of the universe, and that's true, but it's because the universe is full of structure and pattern and symmetry, and mathematics is the language that we have to describe and explain and understand and explore these wonderful things. But as human beings, we enjoy structure and pattern. Our brains take pleasure in them. And so, of course, they are going to appear in our forms of creative expression. And that includes music and art and literature. So it's literature that I want to speak about today. And I want to show you, I hope, some of the ways that mathematics and literature have an enduring conversation, some of these wonderful links. But we can start with structure, because structure is everywhere in literature, and mathematics is the language of structure. So perhaps the most visible place on the surface that structure is apparent in literature is in poetry, because poetry is distinguished, I guess, from prose by having some kinds, one or more, of constraints, whether that's where you break the line, or whether it's maybe something as simple as the precise numerical constraints of various forms of Japanese poetry, like the haiku form with its exactly 17 syllables, and split further into, sounds or syllables, split into a 5, a 7, and a 5. So that's a really precise constraint, clearly mathematical in nature. But there are many more kinds of constraints. And in poetry that features maybe European languages or English and other languages like that, you can often find things like rhyme schemes where certain lines will rhyme with each other, or the rhythm of the poetry is important. So I want to start with thinking about meter, the rhythm of the poetry, because that involves some of the earliest intersections between poetry, literature, and mathematics. So in various forms of poetry, there's a certain rhythm. So I've just got two examples here from famous poems in English or famous pieces of writing. The top one here is from Shakespeare's Romeo and Juliet, and it's got these iambs, they're called unstressed and then stressed syllables, but soft, what light through yonder window breaks, emphasizing the stresses in a very not poetic way there. So unstressed and then stressed. And then if you want that the other way around, Mr. Edgar Allan Poe gives us quoth the raven. So stressed and then unstressed, heavy and then light. So one of the earliest questions that mathematicians and poets, often the same people at that time, asked was, what are the possibilities? And this is what mathematics does so well. What possible meters, poetic meters, can we have of a given length? So for 2 syllables, for instance, if you have 2 syllables, you can have soft and then hard, or unstressed then stressed, like in the first example there, or you can have it the other way around. Actually, there are 2 further possibilities, which are less common, but they are used. So you can have 2 unstressed syllables, or you can have 2 stressed syllables. So actually 4 possibilities. And of course, mathematically speaking, it's pretty clear why that is. We can ask a more general question, and this is what mathematicians and poets in India were asking over 2,000 years ago. So Pingala, for example, in his Chanda Sutra, which is like a treatise on poetry and mathematics, which was added to later over time by different authors. It's very difficult to date precisely. We don't have the original texts. We just have sort of echoes of them and later additions and copies. But even back as far as that, they were looking at what are the possibilities for meter. And in Sanskrit poetry, the syllables are lagu or guru. And lagu is the sort of unstressed one, the light syllable, and guru is heavy or stressed. So what are the possibilities, asks Pingala. Not exactly in this terminology, but how many possible meters are there? How many of these patterns are there if you have n syllables in modern language? And so we can answer this quickly, because we can say every syllable is either lagu or guru, it's light or heavy. So there's 2 choices for each syllable, n choices to make, n syllables, and therefore 2 to the n is the answer, right? So there are 4 possibilities, as we saw already, for 2 syllables. And Pingala gives a kind of recipe for then making the next collection. If we want to make all the possible 3 syllable meters, then we take all of the ones we've got for 2 syllables, which is 4, and we can either add a lagu or a guru to the end of each of those. So we double up, so it would be 8. And actually his description of doing this, it would have needed some symbols. We don't know what symbols were used, but we could think perhaps if we use zeros and ones nowadays with those symbols that we now have, that is giving you kind of something that is resembling binary notation. And something like that then first existed in the context of poetry, which is very cool. You can get more detailed about the question you ask. So Pingala also asks, can we enumerate the number of syllables, the number of meters of a given length in terms of syllables, in terms of how many of those syllables are heavy, the guru, stressed syllable? And he says to answer this, we need to construct what he calls a mountain of numbers. Now, I'm going to show you a picture from a later manuscript, but this mountain of numbers is the one I'm showing you now, which we nowadays often call Pascal's triangle, but it was known about many centuries before Pascal in India by people studying Sanskrit poetry, because Pascal's triangle gives you precisely these numbers. If you go to the nth row and take the kth entry on the nth row, that tells you exactly how many n syllable meters have k of their syllables, these guru or heavy. So that's really interesting that this triangle, Pascal's triangle, emerges again in the context of studying poetry. There's another way, though, that Sanskrit poetry can do this counting. And it's where it's different from the patterns of stressed and unstressed syllables that we have in, for example, in English poetry, because there's a convention in Sanskrit poetry that the lagu or light syllables are shorter in duration than the guru heavy syllables. The convention is that lagu is sort of 1 beat and guru is 2 beats. And so then you can ask, what about how many of these meters are possible, not counting by the number of syllables, but by the duration in time? So if lagu is 1 and guru is 2, we could ask how many meters are possible of a particular duration. And that can also be worked out using a kind of recursive relationship, because you can make a meter of length duration n by taking any of the ones of duration n minus 1 and adding a lagu, a short light syllable, or you can take any of the ones of duration n minus 2 and add a guru or heavy syllable to those, which last 2. And so the relationship you get then is exactly this, that the number of duration n, dn, will be dn minus 1 plus dn minus 2. That is the identical relation that gives rise to what we tend to call nowadays the Fibonacci sequence. But it was known, again, hundreds of years before Fibonacci, and it arose from the study of Sanskrit poetry. So I love that these mathematical ideas are coming from looking at poetry and understanding it. We can really get some fascinating mathematics by thinking about literature. And I hope to show you imminently that this can go in the other direction as well, that literature can get good ideas from mathematics. So it's a two-way conversation. So the meter, the rhythms of the poetry can lead to interesting mathematical ideas. There are other kinds of constraints in poetry. So one more I'll mention is the rhyme scheme. So this is the pattern of which lines rhyme in a poem. And different poetic forms have different rhyme schemes attached to them. So sonnets, for example, there's a variety of possible rhyme schemes. English sonnets often follow the Shakespearean rhyme scheme, but there's another one called the Petrarchan rhyme scheme. I'm giving you an example here. I thought I should, at minimum due diligence, I should give you an example of a Spanish language sonnet. This one I particularly like because it describes how to write a sonnet within the sonnet, so it's kind of fun. But the rhyme scheme here is ABBA, ABBA, CDC, DCD. And what that means is, as you probably know, those A lines must rhyme with each other. So Violante and Delante, the first and fourth lines rhyme with each other. And then as do the fifth and the eighth. So those all rhyme, and all the B lines rhyme, and all the C's and D's, and so on. So it's a simple constraint connecting these lines together. In fact, the number of possible rhyme schemes for a given length of poem is given by what are now called the bell numbers, incidentally. So this is a constraint. Within the rules of the sonnet, then you can be creative and write wonderful poems about anything you like. It does not stop you being creative. Just the same way as in mathematics, having some axioms, it doesn't stop you being creative. It helps you because it gives you something to start from. Once you have your axioms, your rules, your constraints, you then start to explore what is possible. So this is a lovely sonnet. There's a quiz question I like to ask people. Which poet has written the most sonnets? Now, in the English language collection of poetry, Shakespeare comes up high. He's done over 150 sonnets. I don't know if that's a record in English, but I can tell you that it is nothing compared to Raymond Queneau, who produced a little book in 1961, 100 000 milliards de poèmes, which translates as 100 trillion poems, and they are sonnets. So how does he do this? Well, he uses a mathematical idea. He uses the exploding power of combinations. So in the book, there don't appear to be at least 100 trillion poems. What there is in this book is 10 sonnets over 10 pages. Every sonnet has 14 lines. But each of these sonnets respects the same sonnet rhyme scheme. It's slightly different, I think, than the one I showed you, but they all have the same rhyme scheme. But then all of the first lines of the sonnets rhyme with each other. All of the second lines rhyme with each other, and so on. What Queneau has done, in effect, is to create a kind of three-dimensional rhyme scheme, which is brilliant. And it means that from these seed poems, this sort of generating set, you can make others. You can make them by picking any one of the first lines, followed by any one of the second lines, any one of the third lines, and so on. And some editions of the book help you to do this because the pages are cut into strips, so you can physically make the poem that you want. So then how many poems are there? Well, there's 10 choices for line 1, times 10 for line 2, times 10 times 10 times 10, 10 to the power 14, which is indeed, if you check, 100 trillion potential poems. So that's fun, and it's obviously very difficult to do this, so Queneau has to be applauded for doing this. A natural question, and a fair question, I think, to ask at this point is, it's very clever, but is it literature? Is it art? Or is it just artifice? I think it gets into the category of literature and art because it raises really interesting questions, which are highly relevant. You know, in today's moment of large language models and chat GPT and thinking about intellectual property rights and who has created things, or what in the case of chat GPT, Raymond Queneau wrote every single word of every single one of these poems. But did he write 100 trillion sonnets? If the answer is yes, then how can you be said to have written something if you haven't even read it? Queneau could not have read all of the sonnets that are potentially contained in this book. And I know that because if you do the calculation, suppose you read one sonnet every minute, starting now, we are going to have a very long call because it will take over 190 million years to get through all of them. So no one can ever read all of these sonnets. The odds are, if we just pick randomly, each of us, we will create a poem that has never been read before by anybody. So has Queneau written all these poems? Do they even exist? To what extent do they exist? And what's my input if I make the choice of the lines? Have I written that poem? Or, you know, what percentage credit do I get because I didn't write any of the words and any of the lines? So it's just very interesting to think about these things. And that idea and that interesting discussion, that piece of literature has come about because of the power of, you know, combinatorial mathematics there. So it's very cool. I'm going to give you one more piece of lovely structure in poetry, and then we'll talk about some of the structures that exist in forms of literature outside of poetry, because it really is not just poetry. And that is the lovely form of poetry called the sestina. So this, unusually for a form of poetry, we have a pretty good idea when and where it was invented. It was in Italy. It's got a medieval form of poetry that was created for only the most expert troubadours to be able to create. So a sestina, which comes from the word for six, is a poetic form. A sestina consists of 6 stanzas or verses, each of which have 6 lines. So it's a kind of 6 by 6 structure. And it does not have a rhyme scheme. I'm showing you on the right-hand side of the slide the first verse of a sestina, very well-known sestina by the American poet Elizabeth Bishop, A Miracle for Breakfast. And you can see the words at the ends of those lines do not rhyme with each other. So what is the structure here? What's the constraint? Well, from each verse to the next, those exact same words are used, those end words are used in every single verse, but they are permuted, they are shuffled in a prescribed way to get from one verse to the next. And the same shuffling is repeated from one verse to the next, all the way through the poem. So I'll show you what that shuffling is with numbers. So if the numbers are 1, 2, 3, 4, 5, and 6, those represent the end words. Then what you do with this kind of corkscrew spiraling process, you start from the end and work backwards, 6, 5, 4. And then you interleave with starting from the beginning and working forwards, 1, 2, 3. So it would go 6, 1, 5, 2, 4, 3. That's the new order of the words. So we can see this happening in the example I'm showing you. So in this first stanza or verse, the order of those end words is coffee, crumb, balcony, miracle, sun, and river. So we're now going to apply this process. So we go from the end and work backwards, river, sun, miracle, and we interleave with starting from the beginning and working forwards, coffee, crumb, balcony. So we will get the new order for verse 2 will be river, coffee, sun, crumb, miracle, balcony. And there is the second verse. I should say at this point, if you don't know this poem, I am not, doing it justice poetically. I'm showing you the structure, but it is a really good poem and it's well worth reading at your leisure, after this meeting. So this is the second verse. And then to get the end words of the third verse, you do that exact same permutation again in the order in which they now appear. So these same 6 words appear in the third and subsequent verses. By the time we get to the 6th verse, and sestinas have 6 verses, this is the order that we have. I'm just going to see if I can move this out of the way. So that's the order we have in verse 6. And now it's crumb, miracle, river, sun, balcony, coffee. Now I've said they have 6 verses in a sestina. If we were to try and make a 7th verse, doing this same permutation, what would happen? So again, we go from the end and work back, coffee, balcony, sun, and into leave mixed with working from the beginning. So crumb, miracle, and river. So we would get this ordering: coffee, crumb, balcony, miracle, sun, and river. And if you look carefully, you will notice that this is exactly the same order as the original verse. We have retrieved the original ordering of the words. So there isn't a seventh verse because verses 1 to 6, those first 6 kind of permutations we've got everything. We've got all of the possibilities. And then we've got to the end of the cycle, and then we go back to the initial order. So it's a really lovely kind of closed thing with all of the possible permutations you can get with this particular rearrangement represented. Each of the 6 words appears at the end of in every possible position. So all of the words appear at the end of line 1 at some point, all of them at the end of line 2 at some point, and so on. So it's this really lovely structure, 6 by 6 by 6 kind of structure. I should say, typically in a sestina, you kind of wrap things up to finish with. You tie a little bow at the end by having this just 3 final lines that include all of those 6 special words somewhere in them. So sestina form is a very beautiful form, much beloved of poets. Now, we are mathematicians. Of course, we are thinking we want to provide new and beautiful poetic forms. I wonder if this sestina form, which is all about the number 6, does this work for any number? Is there something special about 6, or is it just something that would always work? So let's try it for our favorite number. We think, and as mathematicians, our favorite number is, of course, n. So can we write an n-ina? Does this work in general? So, okay, what would that mean? That would mean n stanzas or verses, or each with n lines, and then these end words, these n end words that we would have, would be shuffled around, and we hope to get this nice structure. So let's try it for, let's say, n equals 4. Let's see if we can write a quartina. I've picked 4 random words, not very random. Let's say our end words are north, east, south, and west, the compass directions. And try this process. So what do? We start from the end, west, and then from the beginning, north, and then work back from the end, south, and then east. So for our second verse, these would be the order of the end words: west, north, south, east. Okay, for our third verse, same process again. Start from the end of the order we now have, east, and then we go west, and then we go south, and then we go north. Okay, that's verse 3. That's the ordering of the words that we would have. Let's try the fourth and final verse. What's our ordering going to be? Start from the end, north, and then beginning east, and then south, and then west. Now, unfortunately, you may notice we've got back to the beginning too soon. The fourth verse retrieves the same word order as the first verse already. I mean, it's too soon. So we only have 3 different verses here, which is bad. And there's another bad thing related, which is that you'll notice the third word, south, never moves. It's just boringly fixed in place. So that it's no good to have a fixed point like that. That makes everything uneven, and that we don't have this lovely property of the sestina where every word appears in every position exactly once. So this is terrible, and we must never ever try and do this. This is not going to work for n equals 4. So of course we want to know, well, which numbers does it work for? And mathematicians investigated this. So they were thinking about this in the kind of the 60s, 70s, and I think took a while to pin down exactly what the criteria was going to be for when this worked. But there have definitely been some mathematical papers about this. I won't give you the full detail of the criteria for guaranteeing that it works, but I just want to mention there is one lovely kind of number for which it is certain that the n-ina form will work, that you will be able to write one of these. So these numbers are Sophie-Germain primes. Now, you will have noticed that 6 is not a Sophie-Germain prime. This condition, this requirement is sufficient, but it is not necessary. These Sophie-Germain primes, it will always work for, but there are other numbers which it works for that are not Sophie-Germain primes. Okay, so just to remind you, a Germain prime is a number that is prime, and twice n plus 1 is also prime. So 3 works. 3 is a Germain prime because Twice 3 plus 1 is 7, which is prime. So 3 is a Germain prime, but 7 is not, because although 7 is prime, twice 7 plus 1 is 15, which is not prime. So 7 doesn't fit into this category, but 3 does. There's a picture there of Sophie Germain, one of the greatest mathematicians of the late 18th, early 19th century. And it was her work on trying to prove Fermat's last theorem, which led her to work with these particular kinds of prime numbers. And she managed to prove the theorem in the special case where the exponent is what's now called a Germain prime, and actually in much more generality than that as well. But this is the kind of easiest class of numbers that we can describe for which she proved the theorem. So yeah, if we know some Germain primes, we get some more candidates for these n enas. So tri-tenas, n equals 3. I have seen some of those actually in print. I haven't seen, though, let's pick a nice Germain prime. If you want to write a 23 ena, it's guaranteed to work, and I don't know if anyone has ever done that. So, you know, it's a wide open field for you to explore. Okay, so in this we've seen then here with these examples how thinking about poetic meter and rhyme schemes and the sestina form can lead to interesting and fun mathematics, and it can also lead to interesting and fun poetry. I want to now give some examples of structure, mathematical structures that have been used in literature more broadly, in novels, in books, and these give us examples of where ideas from mathematics have been successfully used to give a really rich and interesting form and structure to pieces of writing. So the first example is The Luminaries. So this is a wonderful novel by Eleanor Catton. She's a writer from New Zealand. This book came out in 2013, and it's a wonderful book. In terms of plot and story, it has everything you could want. Okay, so it's got love and murder and betrayal and opium and a mystery of some stolen gold and intrigue and all of the good stuff. It's set in a gold rush town in New Zealand in the 19th century. One of the themes of the book, the major themes, is the interplay between chance and fate and destiny and free will and the extent to which we are in control of our lives versus events that, you know, are beyond what we can understand, influencing everything around us. So loosely tied in with that, Eleanor Catton incorporates some ideas from astrology into the book. So, for instance, there are 12 key characters, each of whom is in some way linked to or associated with one of the 12 signs of the zodiac, and some of their decisions and actions she makes be determined by, you know, the position of the stars in the night sky at the event time of the events. Not that she necessarily believes in astrology, but, you know, this is a prism through which to investigate these ideas of free will versus fate. The lead characters, well, the lead, but two of the main characters, the luminaries of the title, the sun and the moon, they are the lovers of the story, and their fortunes kind of wax and wane through the book to mirror the waxing and waning of the moon. And the mathematical constraint that she uses, again, ties in with all of these ideas, because she divides the book into 12 sections or chapters, and to mirror the waning of the moon, every chapter is half the length of the one before. Now, I mean, mathematically speaking, what you've got there is a geometric progression. It has really profound consequences, not only for the structure of the book, but also how we experience the book. I think it's a really well-used constraint. It's not just randomly chosen. This does add richness to the book and your experience of it. Let me show you visually how this works. So this is the first chapter. And then every chapter is halving and halving. So the second chapter is half of that length. There's chapter 3, half again. Chapter 4. Chapters 5, 6, 7, and 8 are going to fit nicely into there. And then we keep spiraling in. Chapters 9, 10, 11, and 12 go into the remaining gap. And there's still a little gap at the end. So this beautiful spiraling structure we get from doing this, and if you want, you can work out where it would be converging to, shows you instantly one thing, which is that the first chapter is more than half the book. More than half of the total length book is that first huge chapter. But then when you get into this and when you're reading the book, you experience this as the spiraling in of the gears are turning. People's fates are being decided around them. The pace quickens up. Things are happening faster and faster. And by the time you get to that very last, final 12th chapter, which is just a very short conversation between the two lovers, it's set chronologically about in the middle of the action, but we are seeing it last. And so what we see is that, unbeknownst to them, without their knowing it, these two characters, their fate is sealed. They are trapped in this spiraling structure that Eleanor Catton has created with this mathematical sequence. Their fate is sealed. And we see this very clearly, and you get that experience reading the book. But as I say, it's a strong constraint in terms of length. The whole length of the book is determined by that very last chapter. If we say that final chapter has length S, let's say, then we can work out the length of every other chapter from that, because the one before has length 2S and then 4S and 8S and so on. And we double and double and double until 11 doublings back. That gets us back to chapter 1. So chapter 1 is, its length is 2 to the power 11 times that shortest length, the length of the final chapter. And that's 2048. So every single word that Eleanor Catton writes in the last chapter, in chapter 12, forces her to write over 2,000 words in the first chapter. So, she's got to be really careful. Every word counts in that final chapter. We can also, of course, work out the total length of the book. We just have to add up all those powers of 2. And if you add up 1 plus 2 plus 4 up to 2 to the 11, the answer is 2 to the 12 minus 1. And so the total length of the book is this 2 to the 12 minus 1 multiplied by the length of the shortest chapter. Now, that tells us that 2 to the power 12 is fundamental to the structure of this book. It's just, that's what it's all built on. And I like this example because, again, one you could say, and it doesn't mean there's anything wrong with talking about these links and everything, but you might say, or someone might think, well, okay, Sarah, you're a mathematician, you enjoy these structures and patterns and mathematics, and you've explored this structure and you've done this calculation, and that's great, and you've had fun, there's nothing wrong with that. But Eleanor Catton isn't doing any of this. She is not necessarily thinking about this stuff. But I think we can prove and we can be sure that she is. And the reason is, in this case, she leaves a little clue. Remember I said that there was some stolen gold in the story. So there's a court case, a legal case around this gold, and they state in the case the exact monetary value, what this gold is worth. And the number is £4,096. And of course, you will know 4,096 is 2 to the power 12. So that's her saying, I think, look, hey guys, I know what's going on here. I've worked it out. I'm using my powers of 2. I know 2 to the 12 is vital here. That stolen gold is right there, sewn into the very fabric of the book. It's really lovely. So that's just a lovely example from literature that, a mainstream literary novel. We can go another step up, though. There are more sophisticated examples of structure, mathematical structure, that have been used to create literature. I'm going to tell you a little story about my next example, and it starts with a puzzle that was entertaining the French aristocracy a couple of centuries ago. Now, I'm giving you a solution to this puzzle, but I haven't spoilt it for you because there are many other solutions that you can find, over 1,000 other solutions. Okay, so the puzzle is, you take a pack of cards and you are only interested in some of the cards. So you take the 4 highest value cards, which certainly in English language is ace, king, queen, and jack. So that's what the A, K, Q, and J are, of each of the 4 suits. So the 4 suits are spades, hearts, clubs, and diamonds. And that gives you 16 cards. And then the puzzle is to arrange them in a square, in a 4x4 square, so that in every row and in every column, there's 1 of each value. And in every row and in every column, there's 1 of each suit. So for instance, there's one king in every row and every column, and there's one heart in every row and in every column. Okay, so this kind of structure has an implicit extra requirement, which when you have physical cards, you don't need to say out loud, but the implicit extra requirement is that there are no duplicate cards. No pair is seen more than once. So there aren't two King of Hearts, for instance. So every pair is represented exactly once, and in every row and column, you've got one of each suit and one of each value. So this, as I say, there are plenty of solutions to this. After a while, maybe you tire of this game, so you want something a bit more advanced. So there's a bigger version of this puzzle, which was doing the rounds in the imperial court of Russia a few decades later. And this is known as the 36 officers problem. And the 36 officers problem was, you have 36 army officers, and they are split into 6 different regiments and 6 different ranks. So in each regiment, there's one person from each rank, like major and general and lieutenant. I don't know what army ranks are. One of each rank in each of 6 regiments. So you've got 36 officers, and no pair is repeated, just like with the cards. So in regiment 1, you have exactly one major and so on. And the challenge is to arrange these into a 6x6 array, so that in every row and in every column, there's one officer of each regiment and one officer of each rank. So it really is just exactly the same as the card problem, but scaled up to now be a 6x6 question. Now, the card puzzle isn't too difficult, but somehow the 36 officers problem is difficult. And it was so difficult that, in fact, nobody could do it. None of the courtiers could do it. Catherine the Great, Empress Regnant of all Russia, could not do it. So what do you do when you can't do a puzzle like this? Well, you ask a nearby mathematician. And the nearby mathematician, to the great good fortune of Catherine the Great, was Leonhard Euler, who was in Petersburg at the time. Okay, so she asks him, can you sort out this 36 officers problem? And Euler couldn't do it either. And when Euler can't do something, then, you start to think maybe it's impossible. Of course, Euler didn't just stop at, can I do this 36 officers question? He immediately started thinking about these kinds of structures. What sizes of array can they be made for and what can't they be made for? So when can you do this? For n, 36 officers is n equals 6. So he was talking about these squares, and he gave them the name Greco-Latin squares because he had 2 things that might be regiments and ranks for officers, or card values and suits for cards. So one attribute he wrote in Greek letters, and the other attribute he did in Latin letters. So Greco-Latin. And actually the more well-known Latin square that we've probably encountered, that's a back formation from that, in fact. So these are he called them Greco-Latin squares, but nowadays we call these things orthogonal Latin squares. And his question was, in general, for general n, are there orthogonal Latin squares, these structures of order n, of this particular size? So for order 4, that's the card puzzle, yes. He thought it was impossible for n equals 6. You can check it's impossible for n equals 2 very quickly. There's just not enough ways to arrange the 2 things that you have to arrange. You can't do it. Like you can't have a 2x2 classical magic square as well. Okay, so n equals 2, definitely impossible. N equals 6, he couldn't do it, and so it probably is impossible because he's Euler. He proved that you could produce these structures. There are orthogonal Latin squares of order n if n is a multiple of 4, and if n is odd, you can do it. But he couldn't do 2, and well, he knew 2 was impossible. He couldn't do 6, and he couldn't do any of the higher ones. So his conjecture was, these structures exist unless n is 2, 6, 10, 14, and so on. So even numbers that are not a multiple of 4. Definitely correct for n equals 2. And n equals 6, actually, well, that was sorted out a while later. So French mathematician Gaston Tarry managed to prove a rather long and not very amazing proof. I mean, it was one of these proofs by exhaustion. He just had to look at lots and lots of cases and check them all manually. And it turns out, yes, indeed, this is impossible. The 36 officers problem cannot be solved. There's no solution. So it's looking good for Euler, and Euler's a genius, so he never gets anything wrong, except in 1959 it was found And everyone was excited about this, that order 10 orthogonal Latin squares actually do exist. Euler was wrong. And there was a huge fuss about this. These things, there was an example that featured on the front cover of Scientific American in November 1959. You can see it there. It's called there again, it's called a Greco-Latin square back then. These things exist. And actually, worse than that, or I don't know whether it's worse or better, but in fact, examples were found of all sizes from 14 upwards. So actually, Euler was completely wrong about this. It's not his fault. Sometimes it happens, even to the best of us. But if you are an author looking for a structure to use in your novel, that novel being about the topic of failure, what better thing to use than, as Georges Perec did, than a structure that is emblematic of one of the very, very few times that Euler, the greatest mathematician, has failed. And this is what Georges Perec did in his book, Life a User's Manual is the English translation. He used this structure of an orthogonal Latin square of order 10. So how did he use it? Well, the book is set in a Parisian apartment block with 100 rooms in a 10 by 10 array. And each chapter is set in a different room. And the chapters are given a unique flavor to them in the following way. So Perec uses the orthogonal Latin square structure. He has lists of 10 things, attributes. So a list of 10 colors and a list of 10 fabrics. And then he gives each chapter a unique flavor by using the orthogonal Latin squares to make any given pair of those attributes appear in exactly one chapter. So there's exactly one chapter that has, say, yellow silk, and there's exactly one chapter that has, say, blue cotton, right? So every chapter just feels different because of this choice, this use of the orthogonal Latin square structure. It's really, really clever. There's more structure in the book as well, actually. If you've got a 10 by 10 square, and each chapter is set in a different cell or room of that square, how do you decide what order the chapters are going to be in? Well, they follow a knight's tour of a 10 by 10 chessboard. But there's a twist. Remember, one of the themes of this book is failure. The characters keep trying to do things and not quite managing to complete them. And this is enacted in the structure as well, because in fact, there are only 99 chapters in the book. The knight's tour is never completed. And Georges Perec blames for this. He dodges responsibility. He says, the little girl on pages 295 and 394 is solely responsible for this omission. So that's it's rather nice. So this is a really interesting and I think worthwhile use of a mathematical structure in a work of literature that is relevant to the theme of the story. It's not just randomly chosen. It really enriches that piece of literature. So we've got a few minutes left, and in that time, I want to just touch on a couple of the other ways that mathematics and literature can have resonances. So structure we've talked about, and so another way that this can happen, that we see mathematics and mathematical ideas, is in the symbolism, the metaphor, the imagery that authors choose. And I could have chosen lots of examples here. You could think about the symbolism of numbers in folk tales and fairy tales, those 3s and 7s and 12s and 40s that we get, in the Bible, in fairy tales, folk tales. Or we could go to the other extreme. We could talk about, how Proust references the fourth dimension when he's talking about the passage of time, or how Tolstoy talks about calculus when he's describing the sweep of human history. But I thought, okay, on the front cover of the book I've written about this kind of thing, there's a picture of a whale. And the reason is because I really love the mathematical imagery in Moby Dick by Herman Melville. So I'm going to give you one example of that. And that is that he features this lovely curve that it's one of my favorite curves, and that's the cycloid. Here is a cycloid being made. It's a very simple idea. You roll a circle along a line, and you follow a point on the edge of that circle as it rolls, and look at what curve is produced. And you get a bunch of these arches, and that arch-like curve is called a cycloid. So the cycloid was named, in fact, by Galileo. He loved cycloids. He said he'd spent 50 years studying them, and he wasn't alone. At that time, and for the centuries after Galileo, like every mathematician you've heard of from that time, pretty much, and probably some you haven't, studied the cycloid. It fascinated people. So I've just got a few names there. Galileo studied it, Mersenne, Descartes, Fermat, Pascal, Christopher Wren, Leibniz, Newton, everybody. That the statue there, that's the statue of Pascal, of Blaise Pascal, in the Louvre Gallery in Paris. And what's he doing? He's studying the cycloid. He loved it. It got this nickname, the Helen of geometry, after Helen of Troy, the face that launched 1,000 ships. This curve is very beautiful. I'll just mention a couple of its wonderful properties. So the area under that arch, the cycloid arch, that's exactly 3 times the area of the circle that generates it. Lovely. The length of the cycloid arch, that's exactly 4 times the diameter of the circle that generates it. It's Christopher Wren that proved that first. So these very beautiful, simple, precise numerical relationships are lovely. There's another reason that it got the nickname, though, the Helen of geometry, which is that, like Helen, it did cause some arguing. And in this case, it didn't launch 1,000 ships, but people argued about who had proved what first, whose methods were correct, a lot of back and forth and, angry disputes over this curve, which is very, very beautiful. Okay, so where does it appear in Moby Dick? Well, in Moby Dick, as you will remember, Ishmael, the narrator, he has a job on a whaling ship, the Pequod, and he sails around and he has all these daydreams and thoughts about lots of ideas, but many of them are mathematical. And there's this little scene where he is talking about cleaning the tripods. So tripods are huge cauldron-like vessels where they boil the whale blubber. It's a very disgusting job. And then afterwards, you have to clean them. So he's standing in this tripod, he's cleaning this thing with his soapstone, and he says it's a place for profound mathematical meditation. It was in the left-hand tripod of the Pequod, with the soapstone diligently circling round me, that I was struck by the remarkable fact that in geometry, all bodies gliding along the cycloid, my soapstone for example, will descend from any point in precisely the same time. So he just throws in this allusion to the cycloid. And what's he talking about there? He's talking about the famous tortichrome problem, which is to find a curve, if it exists, so imagine a curve, and wherever you release a particle on that curve from whatever height, it doesn't matter, it will get to the bottom in the same time. And that has no right to exist, really. Like, why should there be a curve with that property? It seems impossible. But there is, and it's the cycloid. And it was Christian Huygens who was interested in this. He wanted to make a better clock. And so for that, you need something that always happens in the same time. And he said, could such a curve, is there a curve that does this? And it's the cycloid. So I love this because it's one of those times in mathematics that, you invent something over here, you roll a circle along a line. Why should that solve the tortichrome problem over here for you? But it does. So that's just lovely to see Melville just throwing that in, and just a brilliant mathematical illusion in the middle of the ocean with Moby Dick. So we're going to finish with a final example, and this is kind of another way that mathematics can appear in literature, where you have openly a bit of mathematics as part of the plot, and even maybe a mathematician character. So the book we're going to finish with is Jurassic Park by Michael Crichton, which, it was a movie, in fact several movies, but it was a book first, a novel. Came out at the start of the 1990s, and at that time there were a couple of bits of mathematics that were really so popular, they really caught the imagination of popular culture, and they both feature in Jurassic Park. So one of them is openly talked about by there's a mathematician character whose name is Ian Malcolm. He's played by Jeff Goldblum in the films, memorably, and he studies chaos theory. And so you might remember Jurassic Park involves a team of scientists who work out how to clone dinosaurs, and instead of starting a research institute, which is what they should do, they decide they're going to open a dinosaur theme park, which is very silly. So the mathematician Ian Malcolm says, look, this is reckless and dangerous because chaos theory tells us in a sufficiently complex system, you lose the power to be able to forecast and predict this system from any distance, like a weather system. Small changes in the initial conditions will magnify and magnify, like the butterfly flapping its wings. The little currents of air turbulence will magnify and magnify until, 2 weeks later, you either do or don't get a hurricane. Well, the same thing will happen if you have this complex setup of a theme park with living creatures that you don't understand. So chaos theory tells you not to do this. That's kind of fun. There's a discussion in the book and in the films. The book does something extra though. The book is divided into 7 sections, and these are called iterations. And at the beginning of each section, there's a diagram. And the diagram sort of shifts and changes as you go. Now, this diagram is an example of a fractal, and it's a really great illustration of how we can start with something simple that gets very complicated. The fractal in question is called a dragon curve, and it's made by folding paper. So you fold a piece of paper, unfold it, you get a kind of right angle bend. If you instead do 2 folds and unfold, you get a kind of zigzag. If you do 3 folds, it develops a bit more, 4 folds, and so on. Now you can do this with paper. At some point, it becomes impossible. The paper's too thick. So then you can get a computer to do it. And the iterative step is that at each stage, you take every straight line segment and you bend it. So that's how you make this curve. The 4th picture there on the bottom right, that's what they call iteration 1 in the book. So they've missed out a few initial steps, it's fair enough. But then it's the same process. So the first iteration in the book, that's shown on the left now. Then you get the second iteration and the third. At this point, it's like, well, it's getting a bit more complicated, but we feel like we understand, we could understand it. Here's the 4th iteration, the 5th, the 6th, and then the 7th. And by this point, you're seeing this really amazing structure develop. And this is, an example of a fractal, which again, super popular at the end of the 20th century in the public consciousness. It's got this wonderful self-similarity. You see that whole shape represented at smaller and smaller scales within itself. So this is a great example of, the idea that we encounter often in mathematics, that you can start off with a very simple concept that can lead you to something way more complicated than you could have imagined. And the big lesson from Jurassic Park is, if you don't listen to mathematicians, you will be eaten by a Tyrannosaurus Rex. So I think that's a good place to stop. And thank you very much for listening.
I don't know.
Thank you very much. I really love your conclusion.
Thank you.
If we don't listen mathematician, we are gonna be eaten by the dinosaurs.
I mean, this is the lesson of history.
I mean, those can be poetic dinosaurs, right? We can be eaten by language by itself.
Exactly.
Well, I think your talk has been amazing. It is really a journey along the relations between math and poetry and literature. I see it as a kind of a zoology, like you can see many different species and how they interact with mathematics. And as you say from the beginning, it's a dialogue in both senses, right? Like how they are using mathematics to create poetry and literature, and the other way, no? So I will have this question is, do you know if somewhere they are studying like really seriously this kind of relation? Because these are amazing. I mean, for example, in music, they do this kind of automatic music, no? Brian May, all of these kind of things. So do you know if somebody is studying about this, or somewhere they are doing this kind of studies?
So I think the probably the most important group of people who have really deliberately, consciously thought about these ideas and tried to make new ideas and new literary forms and vice versa will be the Oulipo, the group of, they're mostly French mathematicians and writers. It started in the 1960s. So Raymond Queneau and Georges Perec were members of the Oulipo. So Oulipo stands for the first 2 letters of the words Ouvroir de littérature potentielle, the workshop of potential literature. And they actively thought about these links. They're still going, but the heyday was in the 60s and 70s. They thought about these links. They thought about, the literature as structured in the way that, Hilbert made foundations of geometry. They thought about the foundations of literature in this way that kind of, okay, how do we build up a piece of writing? Well, it's like the points and lines and planes. We have letters and words and sentences. And so these are kind of the building blocks. You can impose axioms on any of those. So at the level of letters, for instance, one of the most famous Oulipian works was La Disparition, which is the novel written that doesn't contain the letter E anywhere. So that's an axiom around the letters. There will be no E. So you can add in these constraints and you can explore the consequences. You can explore the consequences of a mathematical theorem in your writing as well. So there's this, let me think, there's a little novelette, I suppose, by Claude Berge called Qui a tué le Duc de Densmore? Who killed the Duke of Densmore? And it's this story where he uses interval graphs to kind of write a detective story. So they were really into, and Berge was, he was a graph theorist. So he was like a mathematician proper, who was exploring these ideas. So yeah, that was a very active group, and there's still activity in those ways. And so there are people, particularly poets, who are interested in, like, how are we using the Fibonacci sequence and how are we using these other mathematical ideas? Someone sent me last week a piece of poetry that's based on the Fano plane. So it's got 7 verses and each verse has 3 lines, and each of the lines appears in 2 of the verses, and that. So yeah, there are these talking.
But all of these are particular initiatives, no? Like there is not like a real study around these, academic or university studies.
Yeah, I think you get people who will have particular interests. So there are people who are doing research into this particular author or this particular bit of mathematics, but that I don't know of like a research group that is doing this stuff. There are some journals. So there's the Journal of Humanistic Mathematics does humanistic mathematics. Yeah, so that actually they're good because they're open source, so you can see everything that's ever been published in there. So they published my paper on Moby Dick. That's why I like them. But they have a lot of thinking about the relationships, the interactions between mathematics and the arts and the humanities. So that is a good place to go to find out more.
So we have a commentary on Facebook. It says it's from Fest Math. It says, very, very interesting talk. Thank you so much. I love the idea of encoding in the structure of poems or novels mathematical patterns. I was wondering about literature, in particular poems, about math structure in its own and furthermore combined with the mathematical patterns within that poem. Have you encountered examples of this?
So wait, so the patterns of the structure, say again.
Yes, about math structure in its own, and furthermore combined with the mathematical patterns within that poem.
So there are, if I've understood correctly, it's kind of, it's the examples of literature which uses the structure combining with the poetic elements. So I have seen, for example, there's a sequence of a set of poems by Jacques Roubaud, I think it is, which uses the Fibonacci sequence in order to have the poems kind of cross-fertilize. So you probably know Zeckendorf's theorem about the Fibonacci sequence, which says that like every number, every positive integer can be expressed uniquely as a sum of Fibonacci numbers, as long as you specify that you can't use consecutive Fibonacci numbers, right? So you can like do 9 is 8 plus 1, but it would also be 5 plus 3 plus 1. So you forbid consecutive Fibonacci numbers. If you do that, then it's a unique representation. So then, with that theorem in mind, he has this collection of poems, 20 poems, and each of them refers, so like poem number 9, for instance, alludes to poems 8 and 1 because that's the Zeckendorf decomposition. So it's using, and it refers kind of to that within itself. It talks about Fibonacci within the poems. So it's very self-referential, both literally and figuratively. So, I mean, that for me is an example of where you've got a mathematical structure encoded in a poem that refers to itself within itself.
Yeah.
Yes.
Yes, in fact, it says that the Fan Opaline poem was also an example, right?
Yeah.
Okay. Well, I think we will stop right now. And thank you very much. It was a really beautiful talk. And well, for an audience, we thank you very much. I will say goodbye in Spanish, okay? And so, muchas gracias a todas y a todos por estar acompañándonos. La próxima sesión la tenemos en 2 semanas, no, la próxima semana, el 14 de mayo. Vamos a tener una sesión especial el 14 de mayo que va a ser de Pedro Alegría, que nos va a platicar sobre matemáticas y magia, un binomio inseparable. Entonces, los esperamos la próxima semana y le agradecemos nuevamente a Sara por her beautiful talk.